Unfortunately, I'm going to let you sleep on many other slides, but this is what I want to discuss with you today. That's the definition of magnitude. You've heard also today about questions about magnitude. What is magnitude? That's a very good question. Well, you have to know that Charles Richter was working in Pasadena since the 20s, where there was a beautiful local network that was very advanced for that time, made by Wood Anderson instruments. Now you do remember that Wood Anderson is a beautiful instrument with a torsion, based on torsion principles, plotting beautiful signals on smoke paper or on photographic paper. And okay, it has a response curve, so it's not flat. It's not like the broadband that we have seen yesterday. Let me jump back and forth between this lecture and what we were supposed to conclude yesterday. I was rearranging a little bit these pictures, and we will go back to this. Okay, for example, in this plot here, that was the one that we were supposed to start from, you see the comparison between the response curve, so the amplitude transfer function of the Wood Anderson short period. Please note here the band, okay, 0.1 and 10. These are hertz. And here you see the long period version of a story. And the broadband now, after the force balance, feedback, whatever principle, it's giving a flat response over a broad band of frequencies. That's why they are called broadband or very broadband. But Charles Richter was using this one. So frequencies were better collected around 1 hertz. But it was the advanced network at that time. Now, I don't know if to continue with this or with other things, but since I told you, let's start with this, let's discuss it. And then he had a problem, because he was living in California. In 1933, there was the Long Beach earthquake. It was magnitude 6 point something, so people was shaken in California. And there were many earthquakes that some people was feeling at the time, maybe from larger earthquakes, but more distant. And so people was phoning to the Pasadena Center, to the Seismolab, asking, is this a larger earthquake? Is this a small one? Should be worried? Oh, Long Beach earthquake, so now we can relax because energy has been released. So he decided to put things in order, just to give an answer to people, to try to classify earthquakes. And what he was doing was to use a sort of millimetric plot by hand. Actually, I found yesterday I don't have it here, I have it in my office, the original plot made by Charles Richter. But here you see a sort of a summary with new name here, because these lines here are labeled with magnitude. But he created this quantity here, because on the left, actually, in the axis, you have the logarithm of the amplitude in millimeters versus distance. So, with this network, he was recording events, and he was using A. So you take really the plot that you have, you take amplitude. So for different events, he was trying to classify, assuming that the source location was known, to plot amplitude versus distance for different events. And he was noticing that they could be classified along lines here. Now, that's logarithmic. And he was looking at line, line, line. So he was saying, okay, if we are pretty much linear as a style here in this part of the region versus distance, maybe we can use this information to classify them according to their different energy. He was knowing that, for example, astronomers were using a similar trick trying to understand luminosity of stars. And he had another piece of information that was the only one available before seismic instruments, and still nowadays is used, especially for historical earthquakes. It's called intensity. So he had intensity numbers that we're going to give a look to it. And then he had these new recordings with amplitudes. And so he decided, okay, can we assign a number to an event in order that I can tell people, no, look, maybe this is nearer, amplitude maybe is larger, but the general average of energy that has been released is smaller according to distance. So what we have here is a plot of amplitude versus distance for different events. Now, no surprise to you that the values are decaying on average. There is no surprise, right? Why, for example? Why amplitude is getting smaller?
Due to geometrical splitting.
That's one, definitely. Definitely, if we consider body waves and surface waves, they should decay with distance due to the conservation of energy. 1 over distance, body waves, 1 over the square root of distance for surface waves. Okay, so they should decay. Any other idea about the possible physical reasons for decay? Just idea, because definitely one we're going to define maybe on Friday or more probably on the next week. Yeah,
the geology of the area could determine and the distance of the source from the sensor.
Yes, but let's say that longer a seismic signal is propagating in an unelastic earth, sooner or later, it's going to lose part of the energy in friction. So unelasticity is another reason. And so, longer you're going to oscillate into an unelastic medium, sooner you're going to lose energy. So unelasticity is another one. What's next? Well, that's a little bit more tricky, but you have to imagine that if you want geology, when the wavefields are propagating into an earth that is not homogeneous, they're going to be reflected, refracted, also by tiny heterogeneities. So they are going to be scattered. So along one direction, there is a third way to lose energy that is scattering, a disordered scattering. And this is going to generate what, for example, you've heard today about coda waves. So, disorder. What else? What else can be here that it can judge maybe not a decay, but some bumps? Also up, but also down. Well, down, but also up. There is another feature that here is averaged. Please do remember radiation pattern, because maybe, especially due to the depth of the source, let's imagine to put these 4 lobes of a radiator. Maybe there you have a larger intensity than here, also if it is nearer. So please do remember that we have source effects into these plots. The modern version of this kind of plots of amplitude versus distance, now they are called GMP, ground motion prediction equations, or until, let's say, 10, 20 years ago, attenuation relationships. And they are used for seismic hazard. But that's a different chapter that we are going to treat in the last lecture of the course. So what we have here is a plot of amplitude versus distance. We are waiting for a decay, but then looking at that, we see a pattern of lines. These lines should separate events with different energy. If we have to imagine first that they are put at the same original distance. So we have to equalize them in some way. Then, given a source in the same position, so considering a receiver at the same distance, then we can try to distinguish energy. Okay? That's why he adopted a standard amplitude. That is the amplitude that is supposed to be radiated by an earthquake at 100 kilometers from the receiver and propagating seismic waves and being recorded in California, okay, and on a Wood-Anderson instrument. Richter was very aware of the limitation of his definition because he was aware that he was using a specific instrument. And all the correction, because he was using tables to make these corrections with distance for equalizing earthquakes and trying to put them all together at 100 kilometers. So he was very well aware that this definition was useful for him because so he can say to the news, okay, no, wait, this is a magnitude 8 in Ecuador, or this is a magnitude 6 in California. Okay, this was the intention. So when the press was phoning to the Seismolab, it could say, no, this was not that large as you feel, as you have been feeling it. So magnitude. That's why nowadays M has an L there that stands for local. Wood-Anderson, California. And the idea is to use the logarithm of the amplitude that you are going to record equalized to a standard A. Okay? And if you want to see that in practice, there you go. Because A0 was defined to be 1 micrometer on a Wood-Anderson. Okay? So it was using that amplitude. It was a signal a little bit above the noise for a Wood-Anderson. Okay, so you could compare all the other ones respect to that A0. A smaller amplitude, of course, should give a negative magnitude with that definition. But actually, he was not able to record them because they were behind the noise. Okay? So magnitude 0 was a reference normal earthquake. And as you can see here, for example, and now we are going to give a look to these two signals here. Let's imagine that we have two earthquakes. And you see, they are totally different. Look at the amplitude in millimeters, may be recorded by the same instrument, that is a Wood-Anderson. So you stay there, you give a look to them, and you say, wow, they are different. Can we measure this difference in terms of energy, imagining that we have to place them at the same distance in some way? That's the correction in that formula. Well, the first thing that you can do is try to use the first arrival of P, the first arrival of S. It was not easy. It was made by hand at the time, no computers. From that difference, as you have done in some way in one of the homework in your wave physics course, you can guess what is the distance of a source. So you measure P arrival, S arrival, you take the difference, and you have a distance. Then, in practice, he was using these 3 rulers here, and these rulers were designed for California using a Wood-Anderson. So, actually, you put these lines here. And what you do, okay, you measure S minus P, or P minus S, according to you. You put the number, and here you see they are very similar. So the same distance of a source. And then you measure an amplitude. So now that's 10, that's 80. Now you could say, oh, well, definitely different propagation, different waves, because dispersion is there, as you know. So it's a mass there. But these two signals had been filtered by a Wood-Anderson. Okay, he was aware of this. So you measure the maximum amplitude and you draw a line. The position and the height of the inner ruler, of the intermediate ruler, was made by him based on California results. And so you see, according to this value here, now you get different numbers. For example, with the distance, if you take 100, if you take 0, you would go here to 1 micrometer. That's the definition. definition. You don't see that. That's millimeters. 0, 1, 0, 0, 1, 0, 0, 1. Okay? So you take 100, 0. Let's imagine that you're crossing the line there. All the other ones are relative to that measure. Okay? That's magnitude. Now, giving a look to this, you definitely understand that nowadays we can do better. Not with the general idea, so to equalize, to take something, to compute a ratio, to take a logarithm. Logarithm is squeezing scales, so we can do better. And we will see how to make it better. For example, we can separate body waves and surface waves, because we know, or we guess, that they are different different expressions of a source and of a medium. So, I started with this definition that was the main concept for today, but now let's go back and let's try to conclude yesterday's lecture. Well, I rearranged a little bit the slides here, but this is just a recap. I was adding here, so we have just to revert something there. Recap of what we discussed yesterday in general terms. Linear system, we know impulse response, convolution, and so on. We know convolution theorem, that is, okay, convolution. You can add many filters here. And if you want, that's the summary of our course. Because we have a source with its time information. We have a medium that is taking the time information and computing body waves, surface waves, reflections, refractions. If the medium is infinite, homogeneous, isotropic, well, we know that this information here is going to be preserved. But if you have interfaces, the time will become a reflection, a refraction, and so on. If we have layers, we can have other waves. If we have dispersion, we can stretch that information. If you have anelasticity, that information is going to be lost in some way. Okay, so if you want, that's the Green's function. Okay, in tiny way. The last one is the signature of the instrument, because we have seen yesterday that most of the inertial seismometers, they have a signature. It's the response function. So the signal that we record on an instrument actually is the convolution of all these filters. And the first thing that we can do is try to remove the last one. And we can do that because we built it. So we know the response of that system. So please remember that the first step in data processing is instrument correction. And you go back here, and that's enough, because we know how messy that part could be. Okay, just another slide that is a summary of one of the items that we discussed yesterday. Please remember that nature is not digital in some way, except some ferromagnetic systems. But with the new, after the 70s, with the new way to collect data and to record, if you want, seismograms, we have the transition between the analogic world to the digital one. And nowadays, the sampling times, as we discussed yesterday, are so small, so short, that in some case, we have to make decimation. We have too many numbers. So, according to the Nyquist frequency, as we discussed yesterday. So still a summary. And this was the slide from which we should start today, but we have already seen it. The summary is here. Traditional instruments, for example, a WWSSM standard station, has two triplets of instruments, short period, long period. What does it mean? Okay, the first ones, usually, they are centered between, let's say, 10 and 100 seconds, or 001, 01 hertz. The other ones are short period. So let's say between, for example, in hertz, between 1 and 10. Wood Anderson, you see, is very effective. It's about 0.8 seconds, so 1 point something hertz. This is very effective. If we use a force balance seismometer, a modern one, and we are so smart that we are no more measuring the motion of the mass, but we measure at each time the force necessary for the mass to stand, so that's a feedback, okay, then we can create tiny instruments that are easily portable, so tiny that I want to show to you two versions. I hope that they've been saved here. No, that's something that was straight. Okay, for example, since I don't want to make any advertisement for private companies, but there are two very famous ones. For example, this is a sort of the amateur model, but it's very similar to the professional ones. And this is the appearance, so the dimension is something like that for a seismometer. I was using this one because there was, let's see if I can, it's not working. Okay, just give a look to this. That part is what we called, in what I was trying to call it in the previous slides, leaf spring. That's a spring, it's minus kx. But so gentle, and the mass is so tiny, because actually we don't need big masses to move, but it's very sensitive. So sorry, it's not working. The leaf spring is this one. And you see the electronics that are around, because they are the responsible to take into account to measure the force needed to that part to stand. So actually nothing is moving there, but we are measuring what is the force necessary to move. So you see, that's the force balance vertical. Force balance, that's the key word. And in principle, it's giving, but what, I was using it yesterday. Okay. Well, I have many others. Circuit, schemes. Now you can understand why in the 70s, this 70s, 80s, these were becoming very popular. If you follow some links about, or if you Google VLANT, you can find also some new. Where it is. STS stands for Stokheisen. And it's the one that is, okay, it's private, but it's so common. That's the appearance. Now, if you open it, you will see here, that's the cap for protection, the circuits. And in one, we can see the leaf spring, as far as I remember. It should be here. There it is. Okay? So you see. And this is one of the most modern seismometers. Wait a second, because if I'm definitely very dumb in instrumental seismology, what I know is the difference between a seismometer and an accelerometer. You could say, of course, it's trivial, but one is measuring displacement, the other one is measuring acceleration. Now, for acceleration, and as you know, when you move from displacement to velocity to acceleration, the signal is getting totally different, from long periods to short periods. And if you think about accelerometers, well, we have them everywhere, inside smartphones or inside airbags. And they are so tiny that this is an old one. I want to show it to you because I like this. Okay, this is about an old version of iPhone, so it's out of the market now. But if you give a look in the circuits, there is something interesting here. It is called MEMS. And MEMS are spread everywhere nowadays. I was trying to ask myself what is MEMS, but okay. I think there is one definition here. It's not here. But definitely acronym. Let's see if it is coming. Okay. micro electromechanical system. Now, if you go back, and they are spread everywhere, you will see that in one part of the circuit, in these MEMS, there are mass and springs, but they are very tiny. Okay, so you can imagine that when you're moving, for example, your phone, part of a small mass here will try to stand by inertia. And what you're going to measure there is Hooke's law. But at this scale, so on a chip-based scale. So an accelerometer, maybe not that sensitive, maybe not that accurate like for professional seismology, is like that, micro. So they're spread, you see the torsion spring. So you can imagine that when you're moving, these tiny masses are trying to stand for inertia there, and you're measuring Hooke's law there. So in real time, you're measuring what is the force necessary for that mass to stand. And you're getting, as you know, there are many free apps you can get, an acceleration. So for example, if I put here by, have you ever tried? No advertisement here. Okay, this is, let me try. But I need a gadget. I'm not sure. Yes. For example, in old computers made by a company, this one, when now the modern hard disks are SSD, solid state. But until, let's say, 10 years ago, all of them, they were using a head that was running, a disk that was running like a vinyl, okay? That was very delicate in case of falling. So there was an accelerometer inside that was letting the hard disk to stop if it was feeling a strong acceleration, just to avoid a scratch of this needle on the head. Just to say that accelerometers are pretty much everywhere. Okay, my telephone is old, but it should have something. Now there are many, that's easy, but just one component. I have another app, let's see if it is working, I'm not sure. It's a long time that I'm not using this one. We can provide these signals to the lady of the seminar to see if it's going to detect the motions. Menus here. Let's see. I'm not sure that if this old telephone is working. Definitely, I'm not sure. Yep. Okay. Uh-oh. Okay, now you can study the Green's function. For example, this has just one component, but okay. And like that. Now you can do that's your homework, okay? Now in the sense that what it's using to plot this signal here is just the accelerometer that we have inside. There are better. Let's see if I can get the other one. Maybe this one. And you can do fast Fourier transform in real time. But I don't remember. Oh, this is very effective also for sound, but that's using the microphone. Sure, this is working. This is a Japanese one. Sensor. Was in real time. Okay, I'm not going to show to you something totally different, but just to show to you the equivalent. Do you see something there? Yep. Okay. Now, you have seen a plot today during the seminar that is similar to this one. Now, on the top, you see the waveform. Now, wait a second. That's not the acceleration of this. It's using the microphone, so it's analyzing now sound waves. Let's imagine P waves. Do you want to make a Green's function study? Okay, let's make Green's function. In the top, you see the waveform in time domain. Then what is running with its peaks is the fast Fourier transform in real time. What you see in the back now, it's time here. Okay. Oops. That's time. And this is the Fourier transform in real time for that part of the signal. That is called spectrogram. So, and the lady, Natalia, was showing many of them. So let's imagine that you have time, it's a S, and then Rayleigh waves. Okay, what you can do is to make the Fourier transform. It will have something like that. That's Fourier transform. But what you can do is also to use time here, frequency here, and according to the different arrivals, you compute the Fourier transform in time bands. So it's like a plot like that. That's frequency, so it should be something like that. And when this is coming, you should have something at a lower frequency. That's called spectrogram. Time, frequency, and the third dimension is giving to you the height of the Fourier transform. And there it is. That's called spectrogram. It's coming from acoustic analysis. What is nice is that for sound, you can easily use it to distinguish between vowels, for example. So if you say, trying to keep the frequency band, the octave standard, so if you say A, E, I, O, U, you see that the patterns of frequencies here are different. Those are called formats. That's in acoustics. P waves. Maybe what we can do is to use a transducer. If I knock on this table, it's not going to show with the accelerometer, but it's going to show the sound. Okay, so it's a conversion. I have another app to show vibrations here in 3 components. That's why I was trying to use it, but I'm not able because please do remember that displacement, velocity, acceleration, they are vectors. So that's why we need triplets. But why am I not using J-shape? I was using a lot of time preparing. It should be working, but it's not. Oh, it's working. Let's see if I can show it to you. Do you see it? Do you see it? No. Because, okay. Well, at least, I'm not sure it is. Okay. So now you can do in this direction, and in this direction. You see that the up-down component, for example, is different. And what is doing this, if I stop this recording, and if I go to analysis, it's doing the Fourier transform in real time. So can you imagine Charles Richter using this piece of information at that time? Okay. So now a silly old smartphone can do a lot of things. Just to tell you that MEMS, now I have to go back, are pretty much everywhere. So to have accelerations, for standard uses, it's easy. Different stuff is to use acceleration for seismological purposes. Let's see if it is working back. Yeah, okay. So this picture has been produced a few years ago, but nowadays MEMS are pretty much everywhere. So to have acceleration is a little bit easier. And to study acceleration could be important for what we call strong motion seismology. Let me go just a little bit slower in this part. So that's another summary of what we discussed. Why I like this one? Because you see these three new lines. STS1, STS2, and GURAB, these are the two, Stokheisen and GURAB, the two main companies that are producing professional seismometers nowadays. And for broadband, you see here that their response curve is practically flat from, let's say, low frequency until 200 seconds, until to frequencies that are easily 10, 20 hertz. So they are flat. What can we do now with these instruments? What a theoretician like me can do with these instruments? Well, now we can try to better understand waveforms, seismic waveforms. So we developed part of a theory with Payne from wave physics and the initial part of this course, trying to understand P waves, S waves, Rayleigh waves, love waves, dispersion, their excitation, and we still have to study elasticity. But we can now try to give a look, if it is still working, to these concepts. For example, let's give a look to this simple, that's not, definitely it's not simple, signal here. Now, when the source is far enough and the noise level is not that high, it's easy to separate body waves and surface waves. And I want to give to you a general message here, for example. Look at the spread in time. So, for example, look at the arrival time here, look at the arrival time here. There are, let's say, 200 seconds or a little bit less than 200 seconds. So this event is very far. So the seismic energy, the seismic wave fields had all the space and time to develop. Now, we can say here that something is totally different than these ones. Look at how sharp are the arrivals of body waves. Look how different are the arrivals of Rayleigh waves. They arrive later. Yes, do you remember a long time ago we discovered that on average Rayleigh velocity is 92% of the S, so they arrive later. And they are dispersed, but they are cylindrical, so that's why they are larger. And they are dispersed. But look also now at the frequency content. Now if you take this part of a signal and this part of a signal, and if you compute the Fourier transform, you immediately get that body waves usually are richer of high frequencies than surface waves. And you can give a look here. You see how sharp in time is this arrival. It's more spiky here. So it will be richer of high frequencies. So this is important. Please remember, if you're doing standard analysis of surface waves, then you're going to do a dispersion study, because that's the most important feature of surface waves. You can use relatively high amplitude signals, but usually they are effective at longer periods than the body waves. Of course, this picture can change a lot according to distances. In short distances, it's very tricky to distinguish between PS and Rayleigh, because they will arrive just there. And maybe dispersion will not be that developed. Okay, so first message. Another message giving a look to signals is that now you can understand how different they appear when recorded on different instruments. You could see, come on, the earthquake is one, the source is that one, the medium is that one. But once you record with a specific instrument, they can appear totally different. That's the short period, all WWSSM. Long period, WWSSM, totally different. Because of course we are sensitive to different part of a signal, of a natural signal. What is funny is that if you take, for example, this is a teleseismic event recorded in Germany, but wait, one of the first ones to be recorded on a broadband. Now with this signal, in principle, you can extract both of them because it's flat. So now you can apply the response curves of the other two and you can simulate an old instrument. That's why nowadays you can still, if you don't have a good Anderson, you can simulate one with a broadband. That's why ML still is used. Another important difference here is that give a look to this one, give a look to this one, and give a look to this one. Now, these are two different long periods, but two different instruments. So different response curves, they are different. This case stands for magnification. So be careful here, because this is 5, this is 2, and this is 20. So part of the signal here is hidden here. But it's not, but it's not visible. In time domain, some feature of the signal can be very tricky. That's why Fourier transform is very important. And as you've seen today, Fourier transform running in time should highlight different parts of the signal. That's why I was plotting, if these are body waves, usually the maximum amplitude should be here and no Rayleigh here. Then here, this peak should be at lower frequency than these ones. So spectrogram can tell you this part of information. Okay, what's next? Another vision of different appearances of the same signal. Now here we're in Arizona, and the earthquake was in Texas, so it's a relatively near event. Now give a look to this. If you remember some of the signals that you've seen today, could be similar, but please take care about the scales here. Because today you're also seeing some signals coming from hours. So what is wiggly in time domain depends on the scale that you're using. But definitely this is very rich of high frequencies. Then we'll give a look to this label here and we'll look short period. Okay. And multiply by 10. What does it mean? That this is tiny once you compare with this and this. And if you give a look to this, it's called broadband. So it contains, in principle, both. But if you give a look to this one, you don't see this. Because actually, high frequency is there, but it is hidden by larger amplitudes that are more evident here. So please, do remember that the vision of a signal depends strongly on the scales that you are using and to the frequency band that you are using. If you are using a broadband, it could be very difficult in some situation to look at the smaller signals that could be, for example, the short period ones. And now one of the final pictures of this lecture about a brief history of seismic instruments and how they decide the appearance. Why I love this picture here? Well, it's a picture that has been recorded associated to the Michoacán 1985 earthquake. It was 19th of September, if I remember correctly. The magnitude estimated, now you know what is approximately magnitude, was a little bit around 8. And that earthquake is very famous in the world, as we will discuss in the final lecture of this course, due to the damage that it caused in Mexico City. You will see in the last lecture that Mexico City actually is more than 300 kilometers from this event. 300 kilometers. Wow, it's a long way. But it killed around 30,000 people in Mexico City. You will see this, that is related to side effects. What I love about this picture here is that these are the recordings, not in Mexico City, but near to the source. And now I want you to give a look to these 3 different triplets, because these are acceleration, velocity, and displacement. Very important, because they are giving to you a flavor of units. For example, acceleration. Okay, for this kind of event, it's quite large, because it is, let's say, 100 centimeters per square meter, per second square, sorry. Now, is it a large value?
Is it centimeter per second square?
Mm-hmm.
It's not.
It's not. Are you sure?
Sometimes we can measure as much as 1 G
Mm-hmm.
acceleration.
1 G.
0.3,
Yes.
0.5.
If you remember in the intro, I was showing to you one of the largest records in Japan. That was 3 G.
Yeah, 3 G.
Wow. So it's not. Let's try to convert it into, for example, the unit that are using the engineers. And we will go back to this concept in the last lecture when we're going to talk about hazard. What about G? How many G is this?
Around 0.1 G.
Right. So it seems not that much. Well, I can tell you that actually 0.1 is not that much, but its hazard will depend about the frequencies that is containing, because the peak, and that is going to be called PGA, peak ground acceleration. This is the parameter that is used in the boost to describe seismic hazard. Actually, that one is 0.1 G. Right. I will show to you in the last lecture of this course that this value can be important for some buildings if the energy is concentrated to the natural period of the buildings. So everything is relative in some way. But what I want to show to you there is that for acceleration, velocity, and displacement, please do remember to, please do remember to use 3 different units. You could say, yeah, it's trivial. Please do remember that for hazard, usually we use G. For standard seismology, we can use centimeters per second square. For teleseismic events, this could be much lower than this. And we can say that this signal here belongs to what was called, or is called also today, strong motion seismology. That's why I was putting this part here. Now, what is strong motion seismology? Well, in the 80s, 70s, 80s, strong motion seismology was the part of the seismology that was related to measure something that is strong. Now, what is strong? It depends on where you are. Strong, at that time, in the original definition, actually, was something that could be felt by humans, so not just by instruments like the first recording of the San Francisco earthquake in Japan. No one was feeling that. An instrument was feeling that, but no one. And so something that on average can be felt by humans has an acceleration, because we are very sensitive to acceleration, is between, let's say, from 0.01 G. That's the threshold. Up to, well, at that time it was 1 G. That's why that's the standard from felt to something that is very hazardous. Instruments that were devoted to record these values were called strong motion sensors. And typically they were accelerometers. And acceleration, please do remember, is reach of high frequency. Okay? So that's why an accelerometric network usually need to go to high frequencies. That's why, and you will see the last picture of this lecture here. Okay, give a look to this. You see that accelerometers want to go towards high frequencies. High compared to what? To the teleseismic ones. So usually they start from 1 Hertz till 10 Hertz, maybe a little bit higher because they are going towards the engineering community. And to measure strong motion, usually they use acceleration, high frequency. And so typically an accelerometric network is not recording 24/7. Usually it's recording when it's triggered. So they can say, oh, something is happening here, they start recording. And so the vision of this signal here is totally different from teleseismic events. Nowadays, strong motion seismology is blurred because actually also a seismometer or a GPS can record something strong. But for acceleration, GPS is not that good. Why? Because sampling, okay, it's nice, but it's sensitive to displacement, not to the acceleration of the ground. So the two extremes of seismological instrumentation can go from GPS to accelerometers. In between, you can imagine to use VBB, so very broadband signals. Now, something more interesting here is that when you go to velocity, you see now that the signal is not that reaching high frequencies. Now you're using centimeters per second, and now you can see some long period signature here. But what is more impressive is that if you have a displacement recording here, now you have centimeters, and that's 1 meter. Now it's 1 meter of displacement, okay? It's strong. And it's strong, especially if you give a look to this. Now I hope you can appreciate the lecture that we spent about the Green's function and when we discussed the near field of the radiation. Because actually it's there. You see that there is a static displacement there of about, let's say, 70 centimeters. So that instrument has been permanently moved in quite a long time here, in 10 seconds. Okay, so in 10 seconds it has been moved permanently by 70 centimeters. If you remove that part, you have here the far field. Please do remember that the near field is decaying very fast. So in some time, this part will vanish. And still is vanished here. So the message about this, that please, maybe you are going to see acceleration time histories, and usually they appear totally different than displacement time histories. All these pictures are trying to show different features of the same event, of course. Some of them are more important for hazard, like acceleration. Why? Because acceleration times a mass gives a force. And an engineer can use a force to design. So that's why acceleration is preferred. So nowadays, the definition of strong motion seismology is a little bit blurred with normal seismology. Let's say is the part of a seismology that is dealing with signals that can be important for hazard. Okay? So it's a more blurred definition. To conclude this part about seismic instrumentation and principles, very simple principles of seismometry, please do remember that we have noise. Now that's a funny definition because until maybe 10 years ago, 20 years ago, the noise had was noise. What is noise? What is not an earthquake? Is, for example, this fan that is running here. Noise could be cars that are passing there. The sea that is bouncing on the coasts, causing the microseisms here, And every station has this peak of noise due to the sea. So it's something that is not an earthquake. Now, what is funny is that in the last 10 years, seismic interferometry is using continuous recordings and it's using noise. So you have to remove the earthquakes to study noise. So please do remember that the distinction between noise and signal is decided about your knowledge and about what you want to do. Maybe you want to give a look to noise. Why? Because noise has no preferred direction. It's isotropic. It's not dependent upon the source, also if it is. But the information is so scattered that you can call it noise. So for example, noise, if two of us are speaking, could be the chit-chat outside. But for them, we are noise. So it depends about what we want to do and what we consider carrying the information. Microtremors that we have seen today for traditional seismologists is noise. It's not the earthquake that I want to study. So just the natural definition of noise usually is related to microseisms, traditionally related to anthropic actions, traffic industry, something like that, and to the effect tradition of the sea. So please do remember that every station has noise on a traditional definition. And that is why when you consider the modern network, like this one, that is, now this is really global. It's not like the WWSSM, it was half, and then we have the other part. Now this is global. It has other adjectives here. It's digital, because now all the instruments are broadband, they are digital. The typical configuration of I was preparing the update, sorry for that. That was 2010, and this is the evolution. Well, not that much, I guess. Well, it seems less than, but that was the update that I was able to find. Here, you should, I think it's still working. Let me check. Yes. So now you have the update until, what is the date? Okay. That's it. But I was showing that to you just to, what's that? Oh, good old wet physics. Okay, just the evolution. And the typical configuration of a seismic net, or the modern one, now is very different from the WWSS. For example, it has two VBB. VBB stands for very broadband. Now you do understand what is a broadband. An instrument based on force balance that is providing a pretty much flat response curve. STS1, STS2, you've also seen how they are made inside. Then there are some ancillary sensors. Some of them are definitely not ancillary. Maybe these are more important than these ones, like GPS. Then you can add a strong motion sensor, traditionally accelerometer. So it's looking at different parts of the signal. And of course, well, you have power, and the communication is no more a pen on a drum, is no more a wire maybe going to an analogic amplifier. Now you have digital data may be transmitted via satellite. So just to tell you, this is the modern seismic network. And the future, and you have seen also today, is array seismology. So to use networks, local networks of seismometers. I wanted to show just two of them, because one has been used by us to show to you the passage of the surface waves at the global scale, the creation of the modes after a strong earthquake. This is the US array. So with a spatial scale of, let's say, a nation. In China now they have a huge, deployment of networks that are communicating together, so they form an array. It's not just a sum of single instruments, they form an array, but they are in some way in phase. On a totally different scale, I like to show this one because this is deployed in the Gran Sasso laboratory for physics. We are studying neutrinos there, so it's in Abruzzo, near to L'Aquila. And there is an array here in the sense that these sensors are connected, and their purpose is to stay there to study, how to say, seismic security for the laboratories of Gran Sasso. So different networks, different arrays. And now really the final pictures for this part of the course. And that's the modern version of this picture here. But I like it, but let's give a look at it after, because it's the summary of what we discussed in these two messy lectures. What do we have here? Well, IRIS is, in some way, the institution that is taking into account the global digital seismic network. And here you see the dynamic range of networks. Here you see the periods that we are interested in. Well, for seismology, definitely, for example, we can go up to here. Let's say acceleration, strong motion accelerometers. Maybe for nuclear power plants until 100 Hertz. That's the limit. Please do remember that in this region here, actually we are already in the realm of acoustics, because after 20 Hertz we can hear. Okay, what's next? This is in period 10 Hertz. Hazard at urban regional scale. Now we are going to longer periods here, until this one, 1000 seconds. Well, 1 hour, it's the longest, is the period of the longest mode of the Earth. So definitely seismology is going here. Then we have longer phenomena, like for example, earth tides. And now we are going here towards geodesy, but it's not my part. What about amplitudes? Well, okay, now we have a huge limit, a huge dynamic range, because we can go to very tiny amplitudes of teleseismic events, up to, for example, accelerations of 3G when we are near to a mega earthquake. So you do understand here that equivalent, it means that it's a measure of dynamic range of the possibility of signals here. It's huge. Let's say from 0, let's imagine that this is, that's meter per second square, so that's 1G, and that's 2G. Here we can go to very tiny events. Please do remember that we have a sort of an inner limit beyond which we cannot go, because there's noise is there, unless you want to use noise. So this is a sort of a threshold of hearing. Lower than this, we can't go, by nature. This was the shadow of the old WWSSN SP, and this is the shadow of long P. And this is the beautiful shadow of modern GDSN, so Global Digital Seismological Network. Because in principle, with VBB, we can cover that part of the periods, that's that part of amplitudes. Still, to have higher frequency, we need accelerometers specified for strong motion. Now, that's the new version of this picture that is more than 20 years old. But why I like it? Because there is magnitude. Magnitude was supposed to be our next topic, also if we define the Richter as well. What do we have here? Well, not periods, but frequencies. So you have the complementary emission. So you see until 100. This is 0.01. Okay, the 3 modes of the Earth. This is the typical noise that we have for a station. And this terrible shadow here was what we could get with a typical network station, like a couple, you can imagine, to join these two ones and to plug them here. That was strong motion accelerometer. It's trying to push here. And we have different lines here, showing what? Well, now it depends on the signal that we want to study. For example, we can study P waves. Now, what about the typical amplitudes of P waves? Well, you have to say it depends on the distance, because we are going to decay, right? So maybe the P wave, let's give a look to this dotted part here. After 3,000 kilometers, maybe we are beyond the noise. Well, it will depend on the energy with which they are being radiated. That's the point. What about S waves? Well, they are larger, and you can see them here. So they appear stronger than P waves in this sky. But again, the message that I want to give to you with this picture here is that actually what we can see or hear or feel depends on the energy with which it has been radiated. Now, after the representation theorem and all other stuff, we understand that one of the best parameters that we can use to measure the strength at the source is m0. That is a force times an arm, with the simplest representation of a tectonic earthquake. Plus m0 minus m0. Moment tensor. But m0 should be the key to understand the energy. And that will be the semi-final answer to what we are going to do. But for today, now, we will make this, no, not this one. We'll make the trip backward. Because now, we have to go to the simplest and most difficult way to measure the strength of an earthquake. It's called intensity. It's called seismic intensity. And to us, to our ears that now we are used to discuss about P waves, S wave, Rayleigh waves, source representation, beautiful instruments. What is this? What is intensity? Well, the answer is simple, but in practice it's very difficult. What is that? Well, for example, this is an event that occurred in 1966 in Barfield, so near to the Seismolab of Charles Richter, and we see dots. And these dots are characterized by numbers. Wait a second, because these numbers, usually they are written with Roman characters. In principle, they should be integer numbers, whole numbers. 1, 2, 3, 4, 5, 6, until, that's the problem. It depends on the scale that we adopt. One of the first ones, well, the most famous in Italy is Mercalli intensity. And actually in US, we are using MM intensity, that stands for modified Mercalli intensity. So it's still there. In Europe, we have been using the Mercalli, the RF that is called the Rossi-Forel, not RF. Then there is Mercalli-Cancani-Seeberg, MCS. Then there is MKS, that has been used in the Eastern Europe. MK stands for Carning, S for Seeberg. Then there is the Japanese. It's a mess. It's a mess. But all of them share one idea. Try to put the numbers in one point according to the effect that the earthquake caused on the human, the social, let's call it tissue or texture. So I go there, I see, okay, someone was telling that they had been shaking. So you go there, you make an interview, okay, how long, any damage here, okay, you put intensity, usually you can put there 3. Then you go into another place and you say, okay, some cracks in the buildings. Then you should ask, which kind of buildings? Wait a second. Masonry buildings or I don't know, reinforced concrete buildings? What about their vulnerability? Now that's becoming tricky. But let's imagine, this is what the new, for example, European scale that is called EMS, European Macroseismic Scale, wants to do is to assume that the building has a normal vulnerability. So each building is assigned to a vulnerability class, and it's normally vulnerable. There is no corruption that was put in the reinforced concrete to be bad. There was no strange effect there. And then you give a look to the damage. and you assign a number. Usually, it depends on the scale, you have 12 degrees, in principle integer numbers. 12 is total destruction, so I hope you will never read 12. But 10, 11 is very strong destruction. 5, 6 is when you feel it, on average, okay? Between those degrees, it depends on how you define them. But all of them are based on, how to say, a campaign where you go there, you look at the buildings, the different kinds of buildings, and then you put a label over a zone. What you do next is try to separate the different numbers with some ISO lines. And what you want to do, in jargon, is to build a macroseismic field. And then you say, okay, the epicenter was here. It's a way to measure the strength of an earthquake. It has a lot of problems. For example, we know that the source is radiating differently, and it's radiating differently, also changing the depth. So the shapes of the isoseisms there should reflect this effect. But there is also the ground that could amplify locally the motion. So maybe you have large spots in some parts, but maybe they are not related to the source, but to the regional conditions, to the site conditions. There is another issue. Maybe some part of the lithosphere is more efficient in propagating waves. And so you will see that these lines should be broader. Or maybe, you will see when we are going to define Q, some parts of the lithosphere are absorbing more. So the ISO lines will be shorter. But these effects are not source effects. So it's not easy to use this one and to say, okay, that earthquake was very energetic. Maybe here there were terrible buildings. In some way, the modern definition of magnitude intensity, is able to take into consideration this effect and should equalize in some way, but it's not easy. So, or for example, as I was telling to you, and you will see this lecture, Michoacan earthquake, and we have seen the signals there, occurred here in the subduction zone. Here there was the sea. No labels there, because actually a necessary condition for intensity to be measured, to be assessed, is that some persons are there. Not on the sea, not in the deserts. So maybe you have a very energetic earthquake in Antarctica or in Sahara Desert, but no one is there to say something. So you can imagine that for Michoacan, the ISO lines were like that. But then in Mexico, but in the scale, Mexico City that was here, we had maybe 11 or 10. Is the earthquake here? No, it was here. Okay? So intensity is a powerful but very difficult tool to be handled. It's not directly associated to energy. It should show the energy, but it's showing also many other effects. So that's why Richter, that was able to collect many intensity fields in California, also after the San Francisco earthquake, was trying to find a new measure. Now wait a second. These slides here, with which we will stop. Okay, for example, this is what I was trying to tell to you. These are two different events, pretty much at the same era. This is called the New Madrid. It's not sure, we are not sure that it was one event or two events, or if any. But let's say it's called New Madrid earthquake. This is San Francisco earthquake. Now look at the ISO lines here. They're totally different. While we will try to understand that this is much broader, because here the quality of a lithosphere is much higher than here, but is highly fractured. So it's more efficient in propagating waves. So energy can travel better here. But if you give a look to the isolines, you could say, wow, Missouri is much more hazardous than California. No. It depends. It's still a tricky definition. So please wait for Q trying to understand these two patterns. Let me show to you, well, we discussed this one. Let me show to you a typical definition of a scaling. Yeah, just one second. Because I want to show to you a typical definition of, this is MMS. So intensity 1, and so on, you see every degree here, and in principle, it should be an integer number, but in some cases with uncertainties. So when you read 7 or 8, 9, it should be 8 or 9. But uncertainties are saying, okay, we cannot say it's definitely 8 or 9. But you see, damage considering especially design structure. So also if one is very nicely designed, it's suffering by damage. Of course, you have to decide. Well-designed frames are thrown out of plan. Buildings, partial collapse. There should be, is there not made by wood? Okay, well-built wooden structure destroyed. So it's a way to decide vulnerability class and then to judge the damage. And when you do this, now can we associate this with what Charles Richter was calling magnitude? Yes and no, because we can have a magnitude 6 in Italy, in the Apennines, near to the middle-aged cities, and if you put the same earthquake in Tokyo, of course, where vulnerability is nothing, intensity would be 5, I would say. 5. Here it could be 9 or 10. So it's not easy to associate, because intensity depends a lot on vulnerability. If you want larger than 5, okay, it's usually giving larger than 6 in intensity. Just to tell you one example that 1 year ago, an earthquake occurred in Ischia. The magnitude was 4, nothing. Well, it caused some victims there, and the intensity in some places was 8. Okay, some could say vulnerability in Italy is terrible. No, not only, but it was magnitude 4, but very near to the surface. So it was leaving a very small set of isolines, but very strong. So it's not easy. If you want, you can use this very rough classification, but this is very rough. Before leaving to you the thing here, please do remember that the definition of Richter's magnitude, that is what we studied today at the beginning of this messy class, is totally connected and tied to a specific instrument. Just to tell you and to couple these concepts with the ones that we discussed yesterday, please give a look to the same event, how it appears on a Wood-Anderson, and this is magnified by 2,800 times compared to what would appear on a broadband. It's totally different. So you see that the largest amplitude here would be measured by Richter here. But actually the largest signal is here. So also the measurement, practical definition of the measurement of the amplitude is tightly connected to the instrument that you're using. That's why Richter's magnitude, that is really a genius piece of work, simple but genius, A over A0, remember that nowadays it's called L because it was connected with an instrument and to California. California that, let me show back it to you, is characterized by features that are not common for other parts of the region, of the country. So that's NL. Yes.
Okay, on the plot,
This one?
No, the second one. No,
I was so messy today that I don't remember which one you're pointing. What was there?
On the log of A over A naught. What is the scientist plot?
Which one?
On this
This one?
Yeah, this one.
Yep.
How did he get those lines? Did he get...
No. Yesterday, you know, I had the book on in my office at the university. Actually, the original plot was not that one. This is a reinterpretation.
Okay.
The original plot, let's see if I... Wait. I'm sure. Richter, magnitude, original plot. It was much better than this, in my opinion. But it was not this. Well, I have it in my book. It's very similar. I have an idea, but you know, I could. Well, if you wait on Friday, I will show to you the original plot. It was a little bit different. It was showing log of A distance, and it was plotting these values for different events. Okay? He had these values. So it was just a plot on millimetric paper. What he was using there, logarithm and distance, was to use lines. They were not on lines, but
he's trying to fix the data.
yes. He was looking at the data of log of A with distance. It was showing like that. So we'll say, okay, can we measure this difference? That's the idea. A difference for logarithm is a ratio of amplitudes. That's the idea. So if you take this, let's separate. So he was saying, look, here the amplitudes are larger than this one. There should be a difference in energy. So he was saying, if we measure this difference, then we get a measure of a difference of energy. Now, the difference between logarithms is a ratio of the two amplitudes. That's why he created here he was putting log of A0. That's why he wanted to define A0. It was a data fitting. Also a terrible one, I have to admit. But actually, if logarithm is linear, it's 1 over r. And it's natural on average. So that was the idea. That's not the original one. Those lines there are more accommodating data. No, I will take to you the book.
Okay, so that was my question. I got it.
Just, you know, I was reading that one yesterday because it's an old book. It has been published in 1954, as far as I remember. And so I was curious about the original plot. So I was going there and I was looking, and it was different than this one. But I had no time, you know, I'm lazy, to make the screen, the digital copy of that paper that is on paper book, and to put it there. But it was more interesting for me. That's why I was trying to say it to you. I don't have the PDF here. I don't think. I'm not sure. I have other things here, but I have this one that is nice. You can try to answer to this one. Oh, what's because it moved. Okay, there is a nice paper. You can read it here. Mathematical questions. Most of them have been answered. Don't worry. It was for GR. I don't have it. Sorry. You have to wait. So on Friday I will take to you the book. One final word about intensity. So you could say, okay, so come on. Please, let's try not to use intensity. Wait a second. It's a very important signature of an earthquake where, for example, you have not a beautiful seismological network nowadays, but it's the only tool that we can use for historical earthquakes. Please do remember that the first recording was 1906 and you've seen it. What about all the other earthquakes? So, historical seismology, trying to read in, well, you have to read into the books to look for chronicles there, to say, oh, in that place, in 2000 AC, something happened. And you put a number there, trying to read, maybe the tower of that, the walls of something was collapsed. That's the only way to get information about historical earthquakes, except paleoseismology. So if you have to dig a trench and look for slip on the faults. Ask a query. But otherwise, intensity is the only signature that we have for historical. Historical means not instrumental earthquakes, except trenching. But you cannot trench everywhere in the world. But if you trench, you can do paleoseismology. So, okay, on Friday we will start with the newer definitions of, newer in the 70s, definition of magnitude, problem saturation, and that. That is the end of it, pretty much the end of the story. Then what we're going to discuss in the final week will be a little bit about anelasticity and scattering, and then tsunami and seismic hazard. Okay, that's the vision of what is left of the course. The slides that you have in your files actually are the same, except a little bit rearranged, because yesterday I was finding a sort of a new logic, or just to put things in order. But at the end of the course I will update also the PDF, but it's pretty much nothing. Okay? Okay, you are supposed to attend the seminar lectures on WED tomorrow in the morning. Am I right or not?
Tomorrow?
Marta Siena lectures.
Yeah.
Okay, he's going to speak about something a little bit more difficult than this. So we are going to see again on Friday. If you remember, but some of the screens are working. Not efficient. Everything depends. Look at this one is perfect. So it's not a ray theory, it's a reflection coefficient. That's, if you don't trust me, it's there. Okay?
Is high.
No, it's. I think it's the surface. Some of them. This is opaque. Okay, this is. What's the English? Qual è l'inglese di opaco? Cioè dark. There is a technical word to describe this kind of screens compared to the new. Some of them that have glassy or something like that. Some of them they don't reflect, but this is reflecting very efficiently. So I don't understand. Huh. Okay. So this one in some ways reflecting. Yes. But not that. Okay.